Hi and Assalamualaikum. My name is NUR LINA BINTI ROSLEE with matrix number CN190057, is supervised by Dr. Nadira Ashraf bin Matnayan. Greetings to panels, technologist Dr. Mazat Ziha binti Ahmad and technologist Dr. Alif Hisham bin Abdul Razak. Today, I will be presenting on the mechanical and microstructural properties of polyvinyl alcohol-based nanofiber enhanced with silver nanoparticles and collagen for cartilage tissue engineering application. My presentation will comprise on the introduction part, objective and scope, literature review, methodology, expected result, and conclusion. We start with the introduction part, which is nanofiber is known as nanomaterials in the nature of one-dimensional solid polymer fibers with diameters ranging from tens to hundreds of nanometers. It is also known as extremely high in porosity, high surface area to volume ratio with numerous possibilities for surface functionalization, great mechanical strength, and flexible characteristics. Polyvinyl alcohol is known as a synthetic polymer that is hydrophilic, non-toxic, water-soluble, biocompatible, and has good electrospinability and high tensile strength. The silver nanoparticles is also known as a biocompatible and well recognized for their bizarre resistance to antibacterial activities, while collagen is known to be enhanced in cell adhesion and promote differentiation of precursor cell into bone-forming cells. It is capable to support the biological activities of MSCs and articular chondrocytes. Mainly, this study is focused on the fabrication of the PVA with silver nanoparticles nanofiber enhanced with collagen by electrospinning techniques. The mechanical properties such as tensile strength and compressive strength were studied for the selection of the optimum PVA loaded concentration. The objective of this study is to prepare polyvinyl alcohols with silver nanoparticles and collagen electrospun nanofibers using electrospinning method. The second one is to characterize the microstructure and mechanical properties of the PVA-based nanofiber enhanced with silver nanoparticles and collagen. The third one is to investigate the bioactivity properties of PVA with silver nanoparticles and collagen nanofiber through in vitro biomineralization. Next, the scope of the study includes the preparation of polyvinyl alcohol with silver nanoparticles with collagen nanofibers through electrospinning technique by different percentage of silver nanoparticles, which is 0, 1, 2, and 3. The second one is determining the microstructural and mechanical properties of the synthesized fiber via tensile strength, compression test, XRD, FTIR, and SEM analysis. The third one is to analyze the bioactivity properties of PVA silver nanoparticles collagen electrospun through in vitro biomineralization using simulated body fluid for 3 weeks. We continue our presentation in the literature review part. Cartilage is a non-vascular form of supportive connective tissue known for having a strong and smooth properties composed of chondrocytes that generate a matrix of collagen, proteoglycans, and other non-collagenous proteins. There are three distinct forms of cartilage, which were hyaline cartilage, which found in areas such as the dicrotodials joints, fibrocartilage found in knee meniscus and the TMJ disc areas, elastic cartilage such as ear. The condition must be made by an excellent tissue engineering scaffolding to serve the purpose for biomedical application. The first one is to stimulate the extracellular matrix natural environment ECM to be biocompatible and to have adequate mechanical qualities, and to enhance cell contact and endure external stresses throughout the tissue regeneration process. The manufacturing process to create this type of bionic scaffold including electrospinning, solvent casting, freeze drying, selective laser sintering, and 3D printing. Chung, Li, Zhang, and their colleagues reported that synthetic and composite polymers are widely used in cartilage engineering as a result of their greater strength than natural polymers, their ability to withstand the electrospinning processes without any noticeable losses, and their uncontrollable biodegradability. PLA and PGA possess limitations towards the use in repair hard tissues like cartilage, bidirectionally unlined, and layered PLA electrospinets loaded with human meniscus cell in an ECM have almost the same tensile modulus as the human meniscus and capable to maintain the physiological meniscus cells gene expression. Synthetic cartilage also been fabricated by polyhydroxy esters such as PGA, PLA, PCl, and related copolymers since they are well defined and approved by FDA for clinical uses. It is reported that when chondrocytes and human BMSC were planted on PLA scaffolds, they proliferated at the greatest rate of all polymers. Tensile modulus of the PLGA scaffold were human-like to the skin and substantially lower than human cartilage. PCL scaffolds also promote cartilage self-proliferation, cartilage ECM synthesis and deposition, and chondrogenic distinction of various stem cell populations. The experimental procedures start with the preparation of PVA silver nanoparticles with collagen nanofibers blends, which is 10% PVA, 0, 1, 2, and 3% of silver nanoparticles, and 1% collagen. It is followed by the electrospinning of PVA silver nanoparticles with collagen nanofibers blend, with 0.5 ml per hour flow rate, 15 cm needle collector distance, and 20 kV power. The tensile strength test of PVA silver nanoparticles with collagen nanofibers is examined using UTHM with prepared sample 6 mm width and its middle part and a length of 25 mm. It will then be followed by compression test of PVA silver nanoparticles with collagen nanofibers, which is evaluated using a UTM with samples plus minus 28.6 mm in diameter, 650 mm in area, and 12.5 plus minus 0.5 mm in thickness. The microstructural evaluation of polyvinyl alcohol with silver nanoparticles with collagen nanofibers is done by XRD, SEM, and FTIR, while the in vitro biomineralization analysis will be done by observe the HA growth on nanofiber after immersed in simulated body fluid. We will then continue on the report writing on result and discussion, and the final year project will come to an end. To be specific, the characterization on tensile strength of PVA with silver nanoparticles nanofibers is performed under optimal temperature and pressure conditions to determine the material's maximal strength or load capacity. The LR30K universal testing machine is used. The cross-head speed of 500 mm per minute will be then utilized. The sample will be placed between two clamps at a spacing of 25 mm on UTM for 500 Newton load cell. Next, the characterization on compression strength of PVA AGNP nanofiber is done by assessing the load at which failure may occur. The sample will be placed between the two plates and a compressive force was applied to the surface of the nanofiber at a cross-head displacement of 12.5 mm per minute for each 25.4 mm of specimen thickness. After the sample being compressed by 30% of its initial heights, the tests are halted. Finally, the in vitro bioactivity of the nanofiber are studied by the immersion in simulated body fluid solution. The sample will be immersed in 50 ml of the prepared simulated body fluid solution and placed in incubator for 37 degrees Celsius for 3 weeks to evaluate the growth of hydroxyapatite. For every 7th day, the sample will be drawn out from the SPF and dry in the incubator for 24 hours at 50 degrees Celsius. The morphological changes and HA growth of the dry sample will then be observed by using SEM. For XRD diffraction, the XRD angle for the thin film electrospun PVA AGNP collagen nanofiber will be observed by using a grazing incidence diffractometer technique. The sample is going to be monitored with a scanning speed of 2 degrees per minute at an angle of 10 degrees and 40 degrees by using radiation with 40 kV of voltage and 40 MA of current. For FTIR, where the PVA and silver nanoparticles collagen nanofiber with size 1 × 1 cm will be prepared, the nanofiber is then going to be scanned between the wavelength of 400 cm, where the result that will be obtained will be analyzed by using software. The next one is scanning electron microscope. The sample will be prepared by sparta coated them in dry condition with cool for 30 seconds of 18 ME. When sparta coating is applied, the conductive coating material acts as a route for charged electron to remove from the material. The sample will be placed into the SEM and being examined with 1000 times and 10,000 times magnification for surface morphology investigation. The expected result for the study is that the nanoscale in diameter of ECM fibrils as well as their porous nature successful to be replicated by nanofibers obtained through electrospinning. The second one is silver nanoparticles with PVA with collagen nanofibers are predicted to display higher tensile strength and elasticity due to the roles of silver nanoparticles as a nanofiller that being outperform other metal nanoparticles due to their unique optical, mechanical, chemical, and electrical capabilities. The last one is the embodiment of collagen on PVA-based nanofibers itself are expected to imitate the natural cartilage tissue properties following to its biocompatibility requirement, such as the growth of hydroxyapatite, which is the important element in human biological system. In order to address the constraint of the established PVA nanofibers' poor mechanical strength, this work attempted to fabricate nanofiber by employing biomaterials such as silver nanoparticles for mechanical property modification together with the incorporation of collagen towards the PVA AGNP blends. The capabilities of arginine, glycine, and aspartate that contain in collagen which increase cell attachment and help differentiate precursor cells into bone-forming cells may also assist in biocompatibility enhancements. The testing method to study the mechanical properties of the nanofibers are tensile tests and compression tests, followed by the study on the microstructure of electrospun nanofibers, which include XRD, FTIR, and SEM, with the study on the in vitro biomineralization using simulated body fluid. The long-term goal of this research was to determine which of blends PVA enhanced with silver nanoparticles and collagen nanofibers is optimal for cartilage tissue engineering application. Lastly, the study hopes that it will open up a new pathway for knowledge on the biomaterial in biomedical application.